evening, everyone. I'm Sathwika from CSA department. In this video, I'm going to give a presentation on introduction to NumPy in Python. So, what is NumPy? NumPy, it is a Python C extension library for an array-oriented computing, and it is efficient, in-memory, contiguous or shredded. It is homogeneous, but the types can be algebraic, and it is a single element of data type D type. And NumPy is suited to many applications like image processing, signal processing, linear algebra, and plethora of others. So here 0, it's considered as a single element of the data type, that is D type. And NumPy is a foundation of the Python scientific stack. So this is NumPy ecosystem: OpenCV, PySil, NumExpert, Astropy, PyTables, Stats Models, BioPython, Scikit-image, Scikit-learn, Numbers, SciPy, Pandas, Matplotlib, and this NumPy's whole ecosystem. So, a quick start, we have to import NumPy as NP, then A equals np.array of a list of an array. Then we have to print A, where we would get the array as a list of from ranging from 1 to 9. And if we try to reshape 3, 3, then later on we have to print the B. We would get an array of 3 dimension, that is 1, 2, 3, 4, 5, 6, and 7, 8, 9, 3 rows and 3 columns. And later B is assigned with an operation B into 10 plus 4. Then we would get an array of this type. So let's try to implement the program now. For this, let's launch the Jupyter Notebook. So let's upload a notebook. Now, first of all, we have to import NumPy as np, then A equals np.array of list 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have to print A to run this cell. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is displayed onto the output screen. And let's try to implement another. Or else let's try to rechange the code. P is equal to A dot reshape print B. So here we have obtained an array of 3 rows and 3 columns. Next, let's perform an operation on B. let's say C is equal to B into 10 plus 4. Now print C. So each and every term of the array is incremented, I mean, it's multiplied by 10 and later it is incremented by 4. So let's head back to the presentation slide. Now, array shape. One-dimensional arrays have a tuple for their shape, have a 1D tuple for their shape. Let's say it's from 0, 1, 2, 3, 4, 5, 6, 7, 8. They have a shape of 9. And two-dimensional arrays have a two-dimensional tuple. And from 0 to 14, the shape is from 3 to 5. And so on. A three-dimensional array, they have 3D tuple. That is the shape 3, 5, and 4. I mean, the length is 3, breadth is 5, and the width is 4. Here, the length is 5, and the width is 3. While in this case, the width is 3, and the length is 5. The height is 4. Now, array elements type, that is of D type. NumPy arrays comprise elements of a single data type, and the type object is accessible through the .dtype attribute. Here are a few of the most important attributes of dtype objects. Dtype.byte order, it is used to return big or little endian. And dtype.item size, it's an element size of this dtype. Dtype.name, it is a name for this dtype object. And dtype.type, it is a type object used to create scalars, and there are many others. Now, the array dtypes are usually inferred automatically and can also be specified explicitly. Let's try to execute this program. Now, A is equal to np.array. A.dtype. So here we have obtained a value that is N64. And next we shall import now here b is equal to np dot array of 1, 2, 3, 4, 5. Let's say it's 4.567. D is equal to p dot b type. Then we should print D. Here we'll get the float value as 64. Now here if we print A, let's try to run. So here we would get in 64 along with an array 1, 2, 3. Now if we try to print P, so we'd get the float values 1, 2, 3 and 4.567. Now let's head back to the presentation slide. So NumPy built-in D-type hierarchy. The generic, it's Boolean type of object type and number, and then flexible. The number is classified into integer, where integer is further classified into signed integer and unsigned integer. And signed integer is further classified into byte, short int, and the long int. Now this unsigned integer is classified into ubyte, ushort, uint, and ulong int. And further, the number, it is classified into inexact format, like that is floating and complex floating. Floating is further classified into half, single float, and long float, where complex floating is classified into C single, complex, and C long float. Now the flexible is classified into character and void, whereas character is classified into string and Unicode. Now np.date times 64 is a new addition in NumPy 1.7. Array creation explicitly from a list of values as a range of values and by specifying the number of elements. So let's try to implement this program as well. The first one is explicitly from a list of values, np.array of 1, 2, 3, 4. That is, we have to import NumPy as np. Let's initialize the value as a. and then later we shall print A. Now we have to run this. So 1, 2, 3, 4 is displayed onto the output screen. Now let's print np dot a range of say 10. Let's learn the cell. So range from 0 to 9 is displayed onto the output screen. And let's say np dot linspace. It is to specify the number of elements, that is 0, 1, and 5. Let's run the cell. So 0, 0 0.25, 0 0.5, 0 0.751 are printed. And now let's print to get the 0 initialized values. Which is np dot zeros. 2 and 2. And let's try to run this program. So we have obtained zeros onto the output screen. And let's print np dot ones, 1 and 5. So ones are displayed onto the output screen. And let's print np dot empty of 1 and 3. Here 3 to 1 are displayed onto the output screen. Now if we print np dot I of 3, we'd get 1 0 0 0 1 0 and 0 0 1. And if we try to print np dot diagonal of 1, 2, 3, and 4, and let's run this cell. So we'll get the elements, the diagonal elements as 1, 2, 3, 4, and remaining all are paired with zeros. Now let's head back to the slide. So we have implemented all this program of explicitly from a list of values as an range of values by specifying the number of elements, 0 initialized, 1 initialized, uninitialized, constant diagonal value, and multiple diagonal values. Now heading to the array memory layout, the D type, it is of header, and later this header is, it takes value from the array scalar, and all these are ND arrays. Now coming to indexing and slicing. So the array which are highlighted in the red color, that is 0, 2, and if after 2 there is a colon, it indicates the all the values of the 2 are considered, and the values that are highlighted in yellow color, the array of 2 and 1. This now after uh, here after the number 1, the colon indicates that's the end of an array. Now if array 2 and 2 colon 3, if there is a colon between the digit 2, then it is implied as 0. Now NumPy array indices can also take an optional stride, and these are the optional slides, like array of the colon. Here too, it starts printing the last values, and since this indicates the zero value starting from starting from 0, the value which starts from 0, and they have to the values are printed from the end, and the difference and the step value is 2, and here the array 2 and 3, here double times of colon indicates the array, it takes value from the end of the from the end of the array, from the end of the row and from the end of the column. Now array views. Simple assignments do not make copies of arrays, that is same semantics as Python. Slicing operations, they do not make copies either. They return views on the original array. And array views contain a pointer to the original data but may have different shape or stride values. Views always have flags, own data equal to flags. And so let's try to implement this program. And we have to specify a as np.arrange. First of all, we have to import NumPy as np, and later we have to specify a variable a as a range function, and then here we have to print b. Then we have to run this cell. So the array has been printed between the range of 3 and 7, that is 3, 4, 5, 6. And if we try to change a little bit of this, like let's try to run this cell. So now then after this, let's say Then later on, let's try to import num v dot flags dot own data as so it is false, and let's print p value as, say, so now let's head back to the presentation slide. Now here array views contain a pointer to the original data, but they may have different shape or stride values. And here views, they also always have flags dot own data type, which is equal to false. The universal functions ufuncs are NumPy ufuncs are functions that operate element-wise on one or more arrays. Here we have used C is equal to A plus B. So it adds both the arrays A and B, 0, 11, 22, 33, and 44. Ufuncs dispatched to be optimized C inner loops based on the array D type. Now here NumPy, it has got many built-in ufuncs, that is comparison, less than or equal to, not equal to, greater than or equal to, and greater than. And it has got some arithmetic functions or addition, subtraction, multiplication, division, reciprocal as well as square. And it has got few exponential functions called exp, expm1, exp2, log, log10, log1p, log2, power, and square root. And it has also got some trigonometric identities like sine, cos, tan, cosine, arc, cos, arc, tan, arc, sine, and the hyperbolic functions called sine h, cos h, tan h, arc of sine h, arc of tan h, and arc of tan cos h. And it has got some bitwise operations called bitwise and bitwise or, one's complement, and left shift and the right shift. Now it has got uh, and it has also got some bitwise XOR. And the next, it has got logical operations like and, logical XOR, not, and or. And it has got few predicates like is finite, is infinite, is none, is signabit, I mean this sign bit, and then it has got some other built-in functions like app, seal, floor, mod function, round, sign, sign, and the trunk values and sync values. Now coming to access, array method reductions take an optional access parameter that specifies over which access to reduce the access, and none reduces to into a single scalar. Now a dot sum is nothing but 105, and addition of numbers right from 0 to 14. Here access is none. So access is none, it is the default, and access is equal to 0. It reduces into the 0th dimension. Here a dot sum access is 0, and for array of 15, 18, 21, and 24, access is 1. And if access is 0, it reduces into the first dimension. If a dot sum of access is 1, array is 10, 35, and 60. Here access is 0. Now coming to broadcasting, a key feature of NumPy it is broadcasting, where arrays with different but compatible shapes can be used as arguments to ufuncs. Here c is equal to a plus 10. Each value of c it gets incremented with a, that is 10 times. Now here if a is 0, 1, 2, 3, and 4, then each value of a gets incremented by 10. Then c is equal to 10 plus 0, 10 plus 1, 10 plus 2, 10 plus 3, 10 plus 4, so on. And in this case, an array scalar is broadcasted to an array with shape phi. So a slightly more involved broadcasting example in 2 dimensions is c is equal to a plus b, where a has 2 dimension values of 0, 1, 2, 3, 4, 5, and b has got 10, 10, 20, 20, and 30, 30. Now c is equal to a plus b. It indicates 0 plus 10 and 1 plus 10, that is 11, 0 plus 10 is 10, 20 plus 2, 22, 20 plus 3, 23, 30 plus 4, 34, and 30 plus 5, 35. Now here an array of shape 3, 1 is broadcast to an array with shape 3, 2. The broadcasting rules are in order for an operation to broadcast, the size of all the trailing dimensions for both arrays must either be equal or be 1. Let's say for 1D array, it's 3, for 2-dimensional array, 2 and 3. Then result will be the 2-dimensional array, that is 2 and 3. And if there is a 2-dimensional array and 3-dimensional array, 6, 1 and 164, result would be 3-dimensional array, 164. And if for and 4D array and 3D array of 3161 and 214, result would be the 4D array, that is 3264. And coming to square peg in a round hole, if the dimensions do not match up, np.newAccess may be useful. Now in this case, np.arrange of 6.reshape of 2, 3 and np.array of 10 and 100, A into B would result into an value error that operands could not be broadcast together with shapes 2, 3, and 2. And if there is an numpy.newAccess of shape, we would get the output as an array of 0, 10, 20, 300, 400, and 500. So let's try to implement the same program over here. Let's try to import NumPy as NP. And here name is equal to np.arrange of 6.reshape of 2 and 3. Now here b is equal to np.array of 10 and 100. Now C is equal to A into B. We shall print C. Then we shall run this program. So there's an attribute error. Now there's a value error that operands could not be broadcast together with shapes 2, 3, and 2. And let's consider another example of np dot new access dot shape. Let's try to run the cell. So 2 and 1 is displayed onto the output screen. And if we try to run 8 times, then let's try to run this. So 0, 10, 20, and 300, 400, 500 are displayed onto the output screen. Now let's head back to the presentation slide. Now the array methods are the predicates a dot any and a dot all, and the reductions a dot mean, a dot argmin, a dot argmax, a dot trace, a dot cumsum, a dot cumprod, and manipulations are a dot arcsort, a dot transpose, a dot reshape, a dot ravel, a dot fill, and a dot clip. The complex numbers are a dot real, a dot imaginary, and a dot conjugate. Now, fancy indexing that are NumPy arrays may be used to index into other arrays. So let's consider this example. First of all, we would be importing NumPy as NP. Dot range of 15 dot reshape 3 and 5, and we shall print A. Now let's run this program. So a 3 rows and 5 columns of an array are displayed on the output screen. And let's try to import NumPy as NP. And if I is equal to np dot array of 0 and 1 and 1 and 2, And if j is equal to np dot array of, let's say, 2 and 1 and 4 and 4, is equals to a of, then we have to print c. So after we have run this particular program, we'd get the output as 2, 6, and 9 and 14. Let's head back to the presentation slide. So let's try to implement this program as well, which states that Boolean arrays can also be used as indices into other arrays. Let's put NumPy as NP, where A is equal to NP dot range of 15, as we have seen this program earlier to reshape 3 and 5. Then we have to print A. Now here if B is equal to A percentile of 3 equals 0, we shall print B. C is equal to array of B, shall print C. Let's try to run this cell. So for A, we would get 0, 1, 2, 3, 4, and 5, 6, 7, 8 to 10, 11, 12. And for B, we would get true, false, false, true, false, false, true, false, 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 true, and the false, false, true, false, false as a true, false table. And for array of B, we would get 0, 3, 6, 9, and 12. The elements which are divisible by 3, we would get that in an array of, that is C. Now let's try to go to the presentation slide. And now the NumPy functions, they are data input or output, and they're from file, gen from text, load, load text, save and save text. The mesh creation are mgrid, mesh grid, and ogrid. And the manipulation are ensum, hstack, take, and vstack. The array subclasses are numpy.ma, masked arrays, numpy.matrix, matrix operators, numpy.memmap, memory mapped arrays, numpy.recarray, that is used to record array. And there are other sub packages like numpy.fft, fast Fourier transforms, numpy.polynomial, efficient polynomials, numpy.line arg, that is used for linear algebra, Cholesky, det, eigenvalues, invest, LST, SQ, norm, quadrant, and SVD are some other linear algebra arguments. I mean, NumPy.math, it is a C standard library math functions, NumPy.random. It is used for random number generation like beta, gamma, geometry, hypergeometry, log normal, normal, Poisson, uniform, and Weibull. Now, FFT, it is nothing but fast Fourier transforms. So we are importing NumPy as NP, and T is equal to NP dot linspace, that is of 0, 120, and 4000. And now here pi is equal to NumPy dot pi, where signal is equal to 12 into NP dot sine of 3 into 2 into pi into t. And signal is incremented by 6 into NP dot sine of 8 into 2 into pi into t. Here it is 3 hertz and later it is 8 hertz. And the signal plus or it is incremented by 1.5, and np dot random of len of t, that is noise. And this is the FFT of abstract value of np dot FFT of signal. And now here frequency np dot FFT of frequency dot size t of 1 minus t of 0. Let's try to implement this program as well. Now here we have to import NumPy as NP, then T is equal to NP dot linspace of 0, 120, and 4000. Now let's say pi is equal to NP dot pi, and then signal is equal to 12 times NP dot sine of 3 and later signal is incremented times of NP dot sine of 8 into 2 into pi into t. Now signal plus equals 1.5 times np dot random of len of t. Now here FFT is nothing but an abstract value of np dot dot FFT of signal. Now here frequency np dot FFT of frequency, signal size, and tuple of 1 minus tuple of 0. Let's try to print. So this is a frequency. Now let's head back to the presentation slide. So that's the end of the slideshow. Thank you.